Hey, good morning, good afternoon, everybody. We will get started in just a minute. I can see that there are still people logging in, so we'll give them one more minute to get settled, and then we'll start. Thanks. Okay, well, thanks again, and welcome everybody today to our webinar. This is the first of a new series. So today, myself, Apollo Vanderberg, and with me is Michael Fiedler. We've been hosting these on a regular cadence, doing an overview of generative design in Fusion. And last month, for anyone that may have joined, we said that we were going to start alternating in months of office hours where we might do a few tips and tricks and then open up to Q&A for those that have gone through our connected learning content that has been posted online. So, a little agenda. I'll kind of review for those that may be new here as far as, where that connected learning content is, if you'd like to go through it and join again for the next one when we do another office hours session. And then we'll dive into our demo and some of our tips and tricks. So this month we're going to focus on the edit model space within the generative workspace, and some things that may be useful as best practices, and things to consider as you go through prepping geometry for your solutions. As a brief note, upcoming, so kind of as we were mentioning, we are kind of going to every other cadence. So next month we'll kind of resume the general overview of generative design, with the following one in November being another office hours, but being it's also the same week as Autodesk University. We may mix it up a little bit with a few guest speakers, depending on what we can arrange. So we'll kind of have a similar open-ended session with maybe some tips and tricks and a guest speaker. So while I go through this, for the first 15-20 minutes or so on the edit model, feel free to be interactive. Feel free to ask questions as we're going through it. In some cases, while I'm talking about something, it may be better just to spend a few more minutes, while I'm stepping through that live than holding it until the end. So feel free to type your questions into the questions panel, and we'll be paying attention and trying to go through those as we can. So with that, I'll jump into Fusion and generative design. Oh, well, I guess first things first, let me show the content that we're talking about. So, we mentioned this is an office hours for our connected learning content. If you go to our Customer Success Learning Hub, which is customersuccess.autodesk.com, we have a number of different courses and content that are free for you to go through. Under the mechanical engineering section, we have a course, a learning path dedicated to generative design in manufacturing. It's a fairly short course. There's 6 sections. All in all, the whole course might take, maybe 2 hours out of your week if you wanted to step through it and get some background on how to use generative design, some of the key concepts and clicks and picks. So for those of you that have gone through it, we will open up for some questions if there's specific questions you'd like to ask around. And then likewise, as we go forward, we'll have another office hours session later. Beyond this, if there is more learning that you'd like to step through, we've had a couple questions come up on it as well. How do I go beyond this? Are there more sample files? And there are, for those that are not aware, in the data panel, down at the bottom, you'll see our sample section, and there's a whole section dedicated to generative design samples. Some of these are outlined in the help as far as the setup and how to go through it. Some are already ready to generate, as well as existing results that you can just explore through. So you can kind of dive in different phases to kind of see how to leverage the tool. So that being said, the model today that I'm going to walk through is not one that we have in the connected learning or in our sample geometry. It's just one that I put together to kind of showcase some of these details here. So this is a lifting mount that we're going to look at. And depending on what's bolted to these 4 brackets, this item could sit at a number of different angles. So, as we start preparing for generative design, some of our considerations that we need to think about are, those different load cases, where is that load going? What's the range of motion that we might need to deal with for this bracket, as well as what do we want to keep as our preserves. So if you recall, preserves are our geometry that will be part of the final outcome. That's where we're going to be assigning our loads and our constraints. And then, where do we want to have obstacle regions? Obstacle regions being areas that we don't want any geometry. So for example, we would not want any geometry in this range of motion for this bracket. And likewise, maybe no geometry in the holes for any mounting screws or mounting bolts that may be passed through there. So the first thing is that comes up a lot of times is people may be wanting to make those changes here within the design space. And while that is possible, our recommendation is that making any changes in the design space, if this happens to be a part or an assembly that you're working on collaboratively with others, will be seen by everybody else. It will be propagated out into that production geometry. A cleaner way would be to come into the generative design space and go into edit model. And this way here, any changes done within this edit model space don't propagate back to the original geometry, but any changes from the design space do propagate down into this edit model workspace. So this ends up being kind of a great sandbox for making any CAD changes that we'd like specific to generative design. So to kind of start off, one of the first things when we come into the edit workspace is a lot of our associations and a lot of our constraints are actually no longer intact. So if you notice before, I was rotating this orange lever here. at this point, I can just grab it and move it around. And so it's not uncommon that I've seen people, as they're making modifications, accidentally grab a part and shift it. So essentially now skewing what would be their original geometry from what they originally had. So one trick to avoid that is we can come in here to the generative model, and if we right click and say rigid group, what this will do is it actually locks it down. So now everything is kind of in a locked state, and I can't move anything around. So for the casual user, this becomes a little bit easier to avoid mistakes with geometry. Additionally, as we get into this, some might ask, why, what's the value of coming into the edit workspace for making geometry tweaks? And some of that might even be for testing different setups. So as we come in here, we're going to create some obstacles. Maybe we're gonna choose what we're gonna have as our preserves, and we might have different ideas as to where we want to start. So maybe in a first test, this entire bracket, this entire square bracket, is going to be one of my preserves. So another tip here for kind of walking through and keeping a sanity check on how things are organized is coming into the generative model again and creating a new component. And this new component I like to call preserves. And then I do the same thing and do another one for obstacles. Kind of walk through why in a second here. So as I make my geometry tweaks, I'll actually start moving bodies into this preserves and obstacles category. And so these machine interfaces, for example, if those are going to be my preserves, I could move them in and just kind of help organize what I want to keep in those two categories. From a visual sanity check, one additional item is that we can go into our appearances by using the shortcut key A, and under paints, glossy, I'll actually color these things. So I'll say my obstacles are red and my preserves are green. So mimicking the same colors that would happen within as we're assigning preserves and obstacles, but now in the edit space, it allows me to, mentally and visually see what I've already kind of tagged as my preserves and what I'm gonna, tag as my obstacles. So I'll make a couple other edits here, and then kind of continue forward with a few other items. So I mentioned maybe creating some obstacle connectors. So obstacle connectors are a great tool for making bolts. We can have bolt heads. We can choose the size of them, and so these will automatically get tagged as an obstacle when we finish editing the model. But as I mentioned, I want to have a visual representation, so I'll drag that into obstacles. So as we have this all finished, you'll notice I have a couple different generative models here. I have a plate, I have a thin plate, annular, and a brace. We can actually clone these generative models and make those different tweaks to them. As a best practice, I'd actually suggest in many cases to go ahead and finish editing the first one. And as you go to set it up, and I'll do this here real quick, the benefit if you happen to do some of the setup before doing any clones is that when you come back into the edit model workspace, if I clone this generative model because I want to make a perhaps a different preserve region, I'll actually clone all the settings and all the parameters that we've set up through study one. Or however many studies that you have created. So in essence, if you have maybe some ideas on different methods of preserves or different methods of obstacle regions for your geometry, go through setting up the first one and then come back and clone your generative model. And you can copy and keep most of those setup parameters as you go through, making the subsequent ones a little bit easier. And so what we've done here is looked at a number of different ones. So looking at how the original plate might behave as the preserve region, having a number of different obstacle regions for the bolts. I mentioned having one for the entire range of motion for that orange part as it rotates about. It also had a number of bolts and nuts kind of going through to secure it in place. And then there was a bracket that kind of came through here to kind of support the load. So as we go through it, you have a thick plate. I took one to see, again, what happens if we were just to thin out the plate. As we build preserves, we're going to keep the entirety of that preserve as a portion of the geometry. So if I have a thinner plate, then I'm starting off with less mass. And so I'm already lightweighting, our final geometry a little bit. Taking that even further, said, well, what if it was just the annular regions that we were keeping? And then, maybe adding a little bit of structure back and having some sort of brace, between those annular regions. So, the real benefit of this edit model workspace is that we can make all of these geometry edits. We can kind of set this up and use this as our test bed for expanding the different types of outcomes that generative design will produce. So, I'll actually show some of the different outcomes that we got out of this. But one other thing too, to kind of highlight, you might notice that a lot of my preserves and obstacles actually have fillets associated to them. And that is actually another tip here. So I actually have a different geometry that kind of showcase this a little bit. So I did two simple models where we're just pulling two preserves, I should say, where I'm pulling a force axially out here, and this right side, that right preserve was fixed, and then I had a body inside that was my obstacle region, kind of forcing the geometry to be built around it. And so what I want to highlight here is for the preserve, the two different shapes that I did are having a square edge for this preserve or adding a small fillet. So I'll kind of showcase both here. And so the difference between those two, it's fairly subtle from a setup perspective. And even from a results perspective, the outcomes are very similar. But what you see is that by adding fillets to some of our geometry, we can actually help alleviate stress concentrations in the final outcome. So if we kind of take a peek at, I'll start with this one here with the square one, looking at some of the stress concentrations, which by all means is not for this geometry the highest stress concentration, but for this region of interest, kind of bracketing the legend, most of the attachment points are fairly high, 7+ megapascals for how these legs attach into that preserve region. By adding a small fillet, during the edit model stage, if we look at the same locations, we can see that most of the geometry now is actually in the 5 to 6 range, with just a couple small spots kind of hitting in a similar fashion. So from a maybe a recommendation standpoint, depending on how your geometry comes in, so if you think about where your obstacles are and how some of that geometry may have to wrap around and attach to that preserve, having a fillet gives it a different landing area. Rather than trying to choose whether we're going to connect to this surface, or the front face, and how we blend across that sharp corner, we have now a tangential surface that we can kind of blend into a little bit easier. Similar discussions go on for the obstacle regions. So as we build obstacle regions, generative design is going to create geometry that, in a best case scenario, is going to come right up to that preserve, or right up to that obstacle region. So we're going to have, and if we look at it back on this one here, we can actually see this a little bit better in the design side. So, I just had a square edge on this end here, and it kind of maintains that squared edge in the final outcome, right? So part of those rules with preserves and obstacles is the fact that at the end of the day, those obstacles will be maintained in their exact shape. And so having that squared edge in this situation actually ends up causing, the location of our peak stresses in this model. So even from an obstacle standpoint, having a small fillet can help minimize and reduce some of those final stress concentrations that'll come out of your generative design solutions. So I'll pause there. It was kind of a lot for kind of a quick run through. See if you have any questions. I do see one that Mike has already answered around this recording. So today's content is being recorded. It will be posted and sent out to everybody. Generally, as we go through both our prior overview webinars as well as moving forward these office hours sessions, they do get posted onto the customer success website. Some of it does get duplicated onto YouTube, but if you wanted a single source to focus on, and say just keep the customer success website as a focal point.
I shared the link to the customer success website in the chat as well, and then I also gave a direct link right to the learning content that you showed on the generative design topic.
Great. So yeah, as far as as we were talking, back with this here, from an edit model workspace, that's kind of the biggest tips and tricks. The only other one that I might highlight at times is depending on your geometry, right? And this isn't necessarily going to be true for every single one, but depending on your geometry, where you have obstacle regions, so for example, this bolt, or even for this range of motion, this sweep that I have here, in many situations, what I like to do is actually oversize them just by a little bit. So, for example, if this given bolt was, a 25 millimeter bolt, I might actually make the obstacle region, 26 millimeters. And the reason for that kind of comes back similarly to this here, in that, we're going to try and butt up right to that obstacle region. And if we look at the output, so anytime we have, say, an unrestricted output or an additive output, we always get this timeline with the geometry. So, the first one being our preserves, and then our obstacle regions, and then that organic shape. And so the next step is actually to do a boundary fill and to then Boolean out or combine to cut out this obstacle region. And so if technically my obstacle regions are slightly oversized, then this boundary fill is a little less required. And at that point, I can have a cleaner shape by skipping and even suppressing this combine feature. So if you kind of look at it between that and that, we kind of get this sharp edge now because of that subtraction. So in many cases, if I can, I'll oversize that obstacle region, so then that way in my final outcome, I don't need this last step. And then I'll have a cleaner T-spline for modifications, and one that should easily clear the actual obstacle.
It's a good tip. Thank you.
Yep.
We did get a question in from Joel, and he's wondering, are there settings to make the results less organic, more symmetric, or more friendly for machining a final design, rather than almost needing to use an additive manufacturing method to generate something like this?
So yes, there are a couple different things that you can kind of think about. So when we get into, I'll kind of go back here into our actual generative space here. So as you set up the model, remember that our outcomes are going to be based off of what you select, say for manufacturing, for example. And so, if you change some of the details about, on a 5-axis or a 3-axis, what is the minimum tool diameter, or how long is that tool? What's the reach? These will influence the type of geometry that you can get. So for example, if, just to be kind of extreme on it, if I would have had this as a, 1mm tool versus a 100mm tool, the 1mm tool will produce outcomes that can be more intricate, right, and have even more of an organic or ornate shape to them. Whereas the 100mm one, being a little bit more blunt of a tool, will kind of limit, the level of detail and intricacy we can get into. So that's one way that you can control aspects of it from 3 and 5-axis. If your geometry supports it, definitely look at, perhaps like die casting or 2.5-axis, or even 2-axis cutting. So those tend to be notably less organic, with a 2-axis or the 2.5-axis geometry. The other way would be kind of jumping into the study settings and leveraging your synthesis resolution. So as we get into a coarser synthesis, we will have geometry that is a little bit larger. And as we get into a tighter synthesis, we will get into, smaller beam-like structures. I don't know if you have anything else there to add, Mike. Is there a best practice to alter the look and feel of the outputs,
Yeah. I thought
i.e.
that would
more
be good for
organic
everybody.
and branches, shapes? Um, so altering the look, so you can, absolutely, so I kind of, as I mentioned, as you get your outcome, um, and not sure how much everybody has dabbled with it, but you can come in and edit, uh, the organic shape. And so if there are things that you want to change about it, you can absolutely do so. So you have the full capability within Fusion to start modifying this, as you see fit, whether you're grabbing a number of them and trying to thicken it up. Um, you know, in a similar fashion to the prior question around symmetry, there are times where, you know, if we're looking at this model, for example, if I liked, the right side better than the left side, even doing like an extrude cut and then mirroring it, mirroring the side that I liked to kind of guarantee, symmetry about a specific plane. But yeah, as far as modifying the physical geometry for anything that is of an organic output, it would be modifying the T-splines. And at that point, you're taking it to the level that you'd want to. For 2-axis and for 2.5-axis, the way that those geometries are built, you would actually end up with a sketch and extrusions. And so you can then modify the sketch and some of the control points so that you can alter its shape.
All right. Robert asked a question about weldments. I'm not sure that I have a complete grasp on that one. I asked if he could add in maybe a little bit more detail for us. I'm not 100% clear whether that is on input or output side that the question is on.
Okay.
Maybe wait to get a little more detail on that. So if we get on the list, then the next question is, can generative design run on parameters in a parametric model? So you could have a cylinder or a recognizable symmetric shape, but the generative design would optimize the parameters, e.g. OD and ID, to achieve a geometry that meets particular load conditions.
That's a good one. So at this point, I'd say that there isn't a built-in, say design of experiment function to say cycle through those. Some of that you could do, manually. So similar to what I was showing here, where, after you set up the first one, you could clone that generative model and then have a different, ID or OD, for the given load conditions, and then run all of them to see how that influences the results. But it is an interesting ask, and I can we can take that back to our product team to see what their thoughts might be.
Yeah, that's a good one. Robert came back, so I'm going to jump down to the bottom. He expanded on the weldment, and he said that, there in the manufacturing methods, there's additive, there's milling. What about designing with welded sheet metal pieces where it is made from flat pieces? So really, in terms of weldment, we're talking about the outcome, right? Like, how do we take that generative design, or how do we can we influence the generative design so that ultimately we know that we're going to get a weldment out of it?
Yeah, I mean that's an interesting one. So I'd say probably a starting point, just from a concept standpoint, would be we have a nice story posted on our website around Claudius Peters. granted that's a little bit more like plate steel, a little bit thicker, but conceptually it's probably the same. When we get into sheet metal itself, it's a topic that comes up a lot, and different people tend to take it different ways. So like I have my sheet metal and I want generative design to optimize the length and duration of the weldments. And then others that want to do that, but perhaps say if I'm keeping the same thickness sheet metal, what other features do I need to introduce into that sheet metal to either lightweight it or maximize its stiffness, whether it's a rib or a fold, things like that. And so those are all things that I know our product management team are aware of. They're trying to find some of the use cases that make sense, most broadly as people bring it up. At this point, the Claudius Peters story, which is more along the lines of setting up the model and then using the outcomes as design insight to then create your geometry in the same fashion that you have it previously. So creating it from sheet metal pieces and kind of dictating where those weldments go is probably the best path today.
And I am sharing in the chat right now. There's a link to these some success stories that we have, including the Claudius Peters example there. If you'd like to take a look at that, it's a good story. Thank you.
Okay, so with oversized obstacles, how do you determine which outcome has responded well and actually avoided the obstacle region without using the subtract? So realistically, if you have an obstacle region, part of our timeline is to actually do this final combine, which is that subtraction. So this is always going to happen. And so with the oversized obstacle, essentially what that means is if I wanted to, I could come in here and either delete or suppress this feature because I know that I built it large enough that my actual preserve is, or my actual geometry that I'm trying to have in there will fit without issue. So if this maybe diameter was 25 millimeters and I made a 26 millimeter obstacle, then I know that I'm going to have a half millimeter clearance on the radius for the whole thing. And so having that final combine or that final cutout isn't required. If you want to keep it, you can, but again, in some cases you can see that final cutout is kind of creating some additional surfacing. And in this case, since it was a sharp cornered obstacle, a sharp corner into my geometry, that's going to be a location for stress concentrations. If I switch over to, so this is kind of some of the outputs that I got from my model that we were just talking through. Having an oversized obstacle left to right, just means that now if I were to do an interference check, I know that I'm not going to have any interferences between my parts. So in some cases, it's not just, we'll say for the benefit of potentially ignoring the final cutout step, but also just for clearance aspects, right? So I know when I've used similar models like this for trainings before, people might actually create their sweep of an obstacle directly from this face to this face. And so then that means, the geometry we're going to build is going to come up right adjacent to that face. So it's almost going to end up being, a very tight slip fit. And so in some cases, it makes sense to have just a little bit more clearance so that way it's not so difficult to insert whatever it is that you're trying to represent by that obstacle region. I hope that makes sense. If not, feel free to ask a little bit more.
Awesome, thanks.
So this round preserve, perhaps a fully symmetric design would be optimal versus this organic design, but this organic design gives suggestions as to how and where to remove material.
Yeah, related to the parametric question a little
Gotcha.
while ago.
Okay. Yep. So doing some exploration and around sheet metal fabrication, we kind of talked about that one as we were mentioning around
Yeah.
the weldments.
Right. Popular topic. Comes up pretty much every presentation. So
yeah, the short answer, yes, we
yeah.
are looking into it and exploring it. It's just a matter of what our product management team decides on how that need is met.
Right. Right. Yeah. I can't give any more insight into that, but look forward to when we can.
Yeah. And then are engineers using generative design to help come up with new geometries, but then almost starting from scratch with a more traditional CAD design, but using the generative design as a starting point for a new shape, like using the web funnel design in the current example, but in a way that a lathe could turn the piece.
In other words, I think the question is, are people using these outcomes that we get, or are we using it as informational maybe, or as a foundation to using a more traditional manufacturing method, I
Yeah,
think is the question.
yeah. And so, with that, I'll kind of switch to this. So this is actually from, our Recognize overview PowerPoint that we host. But so the answer is yes and no at the same time. um,
That's a
you
fair
know,
answer.
yeah. So I mean, generally we do find that people are kind of hitting these three categories as to like what they're doing with generative design, and so it might be new product design. So maybe they are using the outcomes as a way to ideate, where geometry needs to be, and then kind of using that as the basis for, a more maybe traditional design process, or maybe not. Maybe they're kind of taking, a number of different parts, and trying to see, well, can we consolidate them? Because through part consolidation, that's less parts we need to deal with, less vendors that we have to potentially deal with. Maybe it shortens assembly time as well. So there's a number of things from that avenue, and then the last one is kind of the inverse of kind of like what I was just showing here. We had an existing part and we want to make it better. So can we find a new material, that might allow us to make it cheaper, or make it lighter, make it more cost effective. And so we're kind of leveraging that as a form of exploration.
Joel says, thank you.
Yeah. So yeah, what other questions do you have here? I mean, I can kind of walk through a little bit visually showing some of these different results, just for maybe talking points, but for this model, if it was, we looked at, it was like 7 different load cases, so kind of going from like 90 degrees, in a number of increments to, negative 90 degrees, so across that 180-degree sweep, and kind of tested a number of different, primarily focusing on just these preserves as to like different ways to build them and what kind of geometry came out. So with this plate, we kind of got this shape. And again, even in this one here, even though I did oversize, you can still see, to the prior comment, these fragments here are from that Boolean operation, actually including even this one here, right? So that's the Boolean operation to make sure that my preserve is cut out from or my obstacle region is cut out from the organic shape. And so if I were to get rid of that round, I'd still clear my original part. It just wouldn't have that kind of surfacing there, since my obstacle region was a little bit larger than it needed to be. So this ended up being the plate. And then I took one where I took the thickness of the plate down considerably and left kind of annular protrusions. And what's kind of interesting here is that we actually ended up filling in a lot of the plate back. So the overall total thickness in many areas is similar to that of the original plate, at least centrally located. But where it's mainly different is in this this lower webbing here. This plate actually had a lot more webbing, whereas the thinner allowed it to kind of open up and actually be just a little bit lighter. And then from there, I took it down to the full annular. So this one was kind of interesting into how it kind of built. So I didn't take, we'll say the same manufacturing method from each. This actually happens to be a die cast outcome versus the plate one, which was a 3-axis. So just kind of highlighting maybe some different types of outcomes that come from it as well. And then lastly was that kind of X brace. So, a lot of people tend to think with generative, focusing on different materials and making sure their load cases are there. But sometimes, that variance can also come from, how you might approach the preserved geometry, where you're assigning the loads, what you want to keep. Let's see, will it generate the same design when run twice with the same configuration? Can I set the random generator seed to ensure that? So generally, yes. And you would see that if you go through the connected learning content, for the same setup, for the same model, for the same load conditions and load cases, the types of outcomes that you get for a given manufacturing method will be, very similar to one another. There might be some subtle differences depending on, some of the local nuances with, with a given surface, but generally, it'll be the same, overall, geometry. So yeah, it is consistent in that sense.
Yeah, the only thing I might add to that would be, keep in mind that Fusion's very much a live product. A lot of developers working on the product. We update the program frequently. I wouldn't be terribly surprised if you see maybe some different results between versions of the program, right? Because we add as we learn. So there could be some differences between releases for sure, but
yeah,
sure.
Yeah.
There's a couple questions on symmetry next. The
Yeah.
lever
So
bracket.
why is this one not symmetric? And so at face value, it does look symmetric, but this geometry actually isn't symmetric. So if you look at where the bracket lies, left to right, the mounting face for this attachment point is actually right along the center line, whereas these are not. So inherently, this geometry is not symmetric about the YZ plane or along the x-axis in this direction. So the results are not going to be symmetric in this fashion. And then similarly, there's a subtle variance between this pair and this pair in terms of the distance. So even left to right in this view is not exactly symmetric. So it's close, but it's not exactly symmetric with the way that the bracket that I used for this starting point, the way that one was designed.
Yeah. You're using the latest production version here, or are you using something
Yeah.
internal?
No.
Okay. I think I did hear the other day on our call that in this last release we have symmetry too now, right? I think I saw that up in the
Yeah, we've been
Yep.
putting out as a test. So if you come into preferences, we can talk about this for a second, and under preview features. So for example, die casting is not a default outcome as a manufacturing method. It is currently under tech preview. And so if you'd like to enable die casting, you can check the box and have that enabled. Additionally, we've been exposing more broadly the experimental solver and features. So that's what Mike's referencing. And so if you see this and turn that on, you would have access to some of the details around, leveraging a symmetry plane, and there are a couple other items hidden through as far as looking at alternative outcomes or inertial relief. I think you'll also see it here under objectives, whether we're looking at a displacement objective or modal frequency. So there's a number of things that our development team have been working on and are still actively working on, but it's gotten to a point where they are rolling it out to larger groups to kind of get feedback and insight around how it's working.
All right. And I think we're up to date with the exception of the bottom one there. Will generative design be made available in Inventor?
That's a interesting question, and I don't have an answer for that specifically. One of the difficulties, if you will, with doing that is, to do generative design. If I switch here for a second to the oh, it's because I've modified it. So if you were to look at the outcomes, I had a number of different materials. I had a number of different manufacturing methods. So, all in all, I had, around 100 or 200, outcomes that I was filtering through. And so, when we go to solve that by being built into Fusion, we have access to a number of cloud resources. And so, all of those jobs can, all those different outcomes can be run in parallel. And so if we were to try and run that now locally, it would have to be sequential, right? You'd have to run one outcome at a time. And so it doesn't become time effective for people. So I know that's one of the main reasons. We'll say that it started in Fusion and kind of resides there, is kind of giving that flexibility, and time savings to everybody. I don't know if there are other techniques that our development team have looked at for trying to bring it time efficiently locally, but at this stage I don't believe there's a plan, for moving it to Inventor. Right now it's in Fusion, and we'll see what the roadmap holds as we move forward.
Awesome.
True. Someone else mentioned that Inventor users do have access to Fusion, and through desktop interconnect or through desktop connector, you can bring Inventor parts to Fusion and then leverage that part or assembly directly in Fusion. So that is possible as well. Which goes to the next actual question. It is possible, yes. So you have this data panel, kind of going back to it, your team folder here, you can through desktop connector access that in Inventor, and so things that are saved there can be opened in Inventor, and likewise things that are in Inventor can be shared and opened in Fusion. So if you do your 90% of your work in Inventor, and you want to dabble with this with some of your production geometry, you could leverage that to take it into Fusion, and then do your outcomes, and then when you have your outputs like this, you could save it and then link it back into your Inventor assembly. So one that we missed around symmetry, and getting right at the top of the hour here, so I'll try to see if we wrap things up. For something that's radially symmetric, like a quadcopter housing, is there a way to put in downstream constraints, i.e. a circular pattern of 4, so the underlying ribs are optimized by generating designs that the overall structure is symmetric? So yes and no. Again, it's kind of my go-to for a lot of stuff. So I mean, you can control that. So if I come back into the edit model space here, similar to what I was doing with the preserves, you could do similar from an obstacle standpoint, right? If I wanted to limit where geometry can be created, and I wanted to have so you're talking about a quadcopter, and if this was my top-down view for the 4 green locations where the hubs would be mounted, then at that stage I could design obstacle regions to force geometry only to be built in those locations, or only along certain paths. Additionally, we didn't talk too much about it within this edit model space, but sometimes there's benefits to CADing a starting shape, right? So instead of letting the software dictate how this the initial shape is and then kind of whittle away from there, you can seed that starting shape, and then we will grow or shrink as needed from there. And so sometimes you could actually build that starting shape to be your minimal features, and then have it kind of grow to what's needed to maintain the load cases that you have assigned. But then outside of that, kind of as I was mentioning before, once you have that shape, if your load cases are all symmetric, if one quadrant happened to be, we'll say, better aesthetically for you, then there's no reason why you wouldn't be able to take that and mirror it, to kind of get your 4 quadrants, exactly symmetric. As you move forward, definitely you could also try, with the symmetry, symmetry condition that we're kind of moving forward with.
Yeah, awesome.
Okay.
That brings us up to the hour.
Yeah. So yeah, I appreciate everybody joining today. Like I said, moving forward, we are in this kind of alternating fashion. So, next month we will be getting into another general overview. So if I go back, yeah, here, just to kind of end on that. Next month will be a general overview. But then after that, if you go through the connected learning content and you want to have any specific questions, we will have another office hours, kind of the Autodesk University edition. Okay.
All right.
And yeah, thanks again and enjoy the rest of your day.
Yeah, thanks, everybody.